this particular problem, we are given an object that oscillates in simple harmonic motion. Its precision function is given here in blue. X of t is equal to 4 meters times cosine pi t plus pi over 4. So if you need to pause the video on that, I'm just going to crack on all these different parts here, color-coded for you. Alright, so let's do part A. Part A wants us to find the amplitude, phase constant, angular frequency, and the period. So all you have to do is write your generic function for an object that oscillates. In this particular case, the function given mirrors what an object is, or a mass on a spring system that's being stretched to the right. So here, this is a cosine omega t plus the phase shift. So if I just line up the function that's given in the wording in blue, so as you can see, things line up nicely. So in order to find the amplitude, I'm just going to highlight A for amplitude. And the first term in the function that mirrors this is just 4 meters. So the first part is the amplitude, and amplitude is simply 4 meters. The second part wants us to find the phase constant, or aka the phase shift here. Here, the graph's been shifted pi over 4, which is about 45 degrees. So this is your phase constant or phase shift, and that would just be pi over 4 because it mirrors the term there. So the second part, the A, is simply pi over 4. Okay. The third part wants to find the angular frequency. Well, angular frequency is omega, and as you can see in the function given here, omega lines up with pi. Okay. So in this case, omega is just pi rad per second, or hertz. All right. Other than that, part 4 of A wants to find the frequency, which is f. Well, by definition, f is equal to 1 over the oscillation period. Well, here, I don't know what the period is. What I do know, though, is omega is equal to 2 pi over t. So really, in this case, I can just solve for t, because I need t in here. I need t to find the frequency. So I can just flip-flop. I can just move the t up to the top left, move omega down to the bottom right. So t is just 2 pi over omega. Well, here, I can substitute omega as we found here, where I'm circling back and forth here. Omega is just pi. So instead of saying omega, I can substitute the denominator here, which is pi, and pi on top and pi on the bottom cancels out. So the period for this one is simply 2 seconds. Okay. Well, now that I have the period, I can just plug it into the frequency function. So instead of saying it's 1 over t, I can say frequency is now 1 over 2, and the unit for that would just be hertz, t being 2, and that's it. Or you can say 0.5, it doesn't really matter. So frequency is 1/2 hertz or 0.5 hertz. 1/2 is the same thing as 0.5, okay? All right, so that is the answer for part 4 of A. And then the second way to do part 4 to find the frequency is, hopefully you know this function, is that the angular frequency is simply 2 pi times the frequency. Well, in order to find f, I can just divide both sides by 2 pi. And then I can substitute in pi as well for omega, because that's what we found earlier. So as you can see here, pi on the left side, pi on the right side, simply cancels out. So really, the only thing left here is just 1 is equal to 2f, or you can simply divide both sides by 2, and the pi's will cancel out, and that will leave you just 0.5 hertz or 1 over 2 hertz, which is the same answer. Okay. So it all depends on how you see these problems and what information you can pull out of these functions. I think that'll dictate which route you take. So I just show you 2 different ways to find the frequency there. All right, last but not least, the period. Well, I already found the period. The period I found using the first strategy to find the frequency here is simply 2. So I'm just going to highlight the answer as 2. Okay, so the period here is just 2 seconds. All right, that's part A. Part B here says derive an expression for the velocity of the object at any time. Here, well, I know my x of t function generically is, once again, is a cosine omega t. Here, there's a phase shift because the function has a phase shift given. Well, to find the velocity, you would just have to take the first derivative of x of t. So that's what I wrote here. I just said v of t is equal to x prime of t, which is equal to the derivative of x with respect to t. So on the outside, I put d for derivative, or okay, and then the function for x is given as a cosine omega t plus phi there, and then that's just over dt. And then really, all you have to do is kick in chain rule really quick. So the derivative of cosine is negative sine, and then once you do that, you have to take the derivative of the parentheses with respect to time. So the derivative with respect to time would just leave you with omega, because this is a constant that disappears, and the derivative of omega t would just leave you with just omega. Okay, and then you would just pull that out. All right. Other than that, hopefully if you know chain rule, that I just made sense. If you don't, maybe watch a video on calculus on chain rule or something. All right, other than that, the negative sign comes from the derivative of cosine being negative sign, and omega, once again, from taking the derivative of the stuff inside the parentheses. and sine is the derivative of cosine. Okay, so that is it. So here it says find an expression, so I'm just going to plug in omega as pi because I previously found omega to be pi in part A. Or again, the function tells you omega is pi based on where my cursor at the top right of the screen is going back and forth, right? If you recognize the format, omega matches up with pi, so that would just be pi, and A is just 4. I left out the units here, just save them space. Once again, omega is pi, and then the phase shift here is just pi over 4, and that is it. Okay, that's my function. So essentially, I can find v of t at any time by simply plugging in what the time value is, because that is the only unknown variable in this particular function. All right, and then part C wants us to find the expression for acceleration. So to find the function for acceleration, you can take the double derivative, or you can do x double prime, take the derivative of x twice, or you can take the first the derivative of v of t. So here I just wrote out a bunch of different ways for you if notation matters to you. Other than that, really you're just taking the derivative of v of t to get a of t. So the derivative of v of t is written here. So d once again is on the outside. V of t is negative omega a sine omega t plus phi here. And then that's it. Apply chain rule again, and you should get this particular function. The negative signs stay, and then the derivative of sine is just a positive cosine. So positive times a negative remains a negative, and then chain rule tells you to take the derivative of the stuff inside the parentheses. So the derivative of omega t plus the phase shift here, which is dv to omega, and then you can pull that out. So omega times omega is omega squared, and that's it. So here, omega once again is just pi. I want to carry the square down. A is just 4, and then omega is just pi once again. T just gets carried down because that's your independent variable. And then here the phase shift is just pi over 4. And that is your answer for part C. Okay. Part D. Part D asks us to find the position, velocity, and acceleration at 1 second. So really, I'm just going to use the function I just previously calculated or derived in part, C. So here's D. Well, x of t is pretty light work because the function is already given to us in the original statement. X of t here in blue is 4 meters times cosine pi t plus pi over 4. So I just carry that down. Here I highlighted t for you because it says it wants the position at 1 second. So really I just got to plug in 1 second. Okay. So everything essentially is the same. So here I just made a note, x of t at 1 second. The 4 is carried down, cosine gets carried down, pi gets carried down, t is 1 second, and then the phase shift got to carry down. And then if you do that, here pi times 1 is just pi, and then pi plus pi over 4 is just 5 pi over 4, or you can say 1.25 pi. It's up to you. I just kept that as a fraction here. Okay. Other than that, if you plug this in your calculator, make sure that it's in radian mode, because once again, 5 pi is 5 pi rad. So if you're in degree mode, you will screw yourself over. So I made a note for you here. So hopefully if you're watching these videos, make sure to switch your mode into degrees and radian based on what you're doing. Okay. Here it needs to be in radian mode because it's a 5 pi rad. All right. So make sure you do so. If you plug that stuff in correctly in your calculator, you'll get a value of negative 2.828 meters, and that is your answer for part D for the position. Here, I'm just going to go ahead and crack out the velocity. The velocity function that we derived previously in part C, so if you need to go back to it, really is just omega a sine pi t plus pi over 4, omega being pi, and then amplitude being 4. So if you plug all this stuff in your calculator, you should get a value of about, let me just fast forward all this. This is just plug and chug stuff, okay? A positive 8.886. I left the positive sign out here because a negative times a negative is a positive, and it says the word velocity. So I do need to give you a direction. So in this case, at 1 second, the object is moving to the right because it's positive at a rate of 8.886 meters per second, okay? If it asks for speed, just leave the positive sign out. And then last but not least, to find the acceleration, really it's just plug and chug anymore. We already derived an expression for acceleration, and the only thing really here we have to plug in is just t. So t being 1 second, so I carry everything down. I carry everything down, and the only thing I substitute in, which is 1 second. So if you do all of this in your calculator in radian mode, you should get a value of about 27.92, and that's going to be a positive because if you do cosine of 5 pi over 4 here in radian mode, it will give you a negative number. A negative times a negative will give you a positive. So because it's its acceleration, which is a vector, I do need to tell you which way the object's accelerating. So we say that the object is accelerating to the right at a rate of 27.92 meters per second square at 1 second. All right, that's D. Let's do E and F, almost there. D, find the maximum speed, and then A, find the maximum acceleration. So for this one, I'm not going to prove stuff to you. Hopefully by now you're familiar with these functions. V max here is A omega, and then A being 4, omega being pi, because we found that earlier, or again, once again, the function in blue here tells that omega is just pi. And if you punch this in your calculator, you get a value of 12.57, okay? And that would be meters per second, and it asks for speed, so I don't need to give you a direction. So I'll just say the speed is 12.57. So it can be accelerating leftward or rightward, but at the equilibrium point, the maximum velocity here is 12.57 meters per second. And then the second part of E asks you to find the maximum acceleration. The maximum acceleration here is given by the function a omega square. Once again, a is given to us as 4, omega is just pi. I want to square that. And then if you do that properly, you get 39.4 meters per second square. And here, I don't know which acceleration it wants. It just says find the maximum acceleration. So I know that the object can accelerate left or right. And it didn't use the phrase magnitude, so I would just go ahead and include the plus minus sign here based on what it wants. So I'll just be safe, and I'll say plus or minus 39.4 meters per second square, and that is your maximum acceleration for this particular function. And then F. F wants us to find the displacement between 0 to 1 second. So really delta x here, or aka displacement, is xf minus xi, xf being the x at 1 second, xi being the x at 0 second, which is a starting point. I highlighted x equal to 0 here, or times equal to 0, because I don't know what it is. I already know x at 1 second because we previously calculated, so we need to rewind the video, okay? We already found x at 1 second. I don't know what x is at 0 second, all right? So therefore, I can just plug it in. So here it says x of t is 0 second. Once again, the function is given to us is 4 meters cosine pi. Well, t is just 0, so I want to plug in 0. And then plus the phase shift here, which is given as pi over 4. And if you do all this on your calculator, you'll get 2.83 meters, okay? Do not assume that the object is at equilibrium at 0 second, okay? That's a false assumption, all right? So if you plug in 0 second here, you notice the answer is not 0, it's actually 2.83. So it's a common misconception that folks might think, well, x at the position at times equal to 0 is at equilibrium, and that is a no-no. All right, so just do a plug and check and let the calculator speak for itself. So now that I know x at 0 second, I can use the information found for x at 1 second earlier. So therefore, change in position here, or aka displacement. Well, the object was at, or is at, negative 2.823 at 1 second, and I want to subtract it from another 2.823. Okay, so a negative minus a positive. In this case, you have two negative terms. That just makes a bigger negative value. So the answer here would just be negative 5.656 meters. And that is it for this particular video. I hope that helps. Stay nerdy, don't be whack.